Today, I often say, is one of the probably the most theoretical lecture of the semester, and it is based on the concept of electronegativity. And so we're going to start by defining what that is. We define the electronegativity like this. We define it as being a relative measure of the attraction in atom places on shared electrons. And of course, if we're talking about shared electrons, that means that this is going to be most important to which types of bonds? Is it most important to ionic bonds or to covalent bonds? Well, which one involves shared electrons? Covalent. So it's going to be most important as it applies to covalent bonds. And in particular, we start by looking at nonpolar bonds. Now, I put in parentheses here pure covalent because this is what your author calls them. Your author calls them pure covalent bonds, but most chemists refer to them as nonpolar bonds. And a nonpolar bond is one in which the electrons are shared equally. That's why it's nonpolar, because it's not like one has them more than the other. We use the term polar. It's kind of like our politics today. Seems like if you don't have one view, you have the other extreme view. And so in a polar bond, this is when electrons are not shared equally. And when you came in here today, I had you, if you have your textbook available, open up to page 341 in your text. Page 341 shows a table of electronegativities. And this table is one which omits the transition elements in the center, and for at this level that's fine. We don't need to go very much into depth, and we also do not see electronegativity values given for the noble gases. So in the absence of those, in fact, these don't have electronegativity values because, of course, if we go back to how we defined the electronegativity, we define it as being a relative measure of attraction at atom places on shared electrons. What is it that these elements don't do right here?
They don't share.
Yeah, they don't share and they don't transfer. They don't do anything. They don't form bonds with other elements. Now there are some exceptions. We just mentioned what they are. It does turn out that these three elements, the krypton, xenon, and radon, they do actually, all three of them, bond with fluorine. And the xenon and radon will also bond with oxygen. But other than those exceptions, the helium, neon, and argon, they do not bond with anything. And again, the last three here, the krypton down to radon, they will form bonds with fluorine, and the xenon and radon will bond with oxygen as well. Now, as far as what I'd like for you to know about the table of electronegativities is this. You do not need to memorize specific values. However, I would like for you to know the general trends in the electronegativities. So that is, if you don't have the values available, you should know the general trends. And that is, if we go across from left to right, what happens to the electronegativity values? They increase. And as we go down within a group, what is the general trend? They decrease. So that's what you should know. You should know the general trends. That is, again, the electronegativity values increase as you go across from left to right in the periodic table. The values tend to decrease. I mean, there are some exceptions, but the general trend is that they decrease as we go down within a group. So now, if we go back to how we define these terms, and that is the terms polar bond and nonpolar bond, and if we talk about what these electronegativity values represent, the larger this value, that is, we see that fluorine has the largest value, the larger this value, the greater its attraction for shared electrons. And the lesser the value, the lesser its attraction for shared electrons. So again, big values, big attractions, little values, little attractions. And it should be no surprise when we talk about ions, if we were. Now remember, this is more important when we talk about covalent bonds. But notice with the large electronegativity values, these here are ones that have greater attractions for electrons, is what it boils down to. And the metals here then would have lesser attractions for the electrons. So if we came back then and we wanted to determine the polarity of bonds, let's say that we had a bromine atom bonded to another bromine atom. Now we're just talking about one atom bonded to another. We're not talking about a complete molecule. But if we had one atom bonded to another in these, what we'd do is we'd look up those electronegativity values. In fact, we wouldn't even need to look it up for two like atoms bonded together, because if we had two like atoms bonded together, they would automatically be which type?
Nonpolar.
They'd automatically be nonpolar, because they are going to share electrons equally. Their electronegativity values are the same. So we would say that these have a nonpolar bond, or your author would refer to it as a pure covalent bond. Again, we wouldn't even need to look up the electronegativity values because they would be the same. But if we did, we'd see that all bromine atoms have an electronegativity value of 2.8. Then if we looked at a bond between nitrogen and chlorine, here if we wanted to determine whether it's polar or nonpolar, we come back to our table of electronegativities. We see that nitrogen and chlorine both have a value of 3.0. They both have a value of 3.0. This bond here is going to be nonpolar once again. And then if we looked at a bond between sulfur and fluorine, we would see that sulfur has an electronegativity of 2.5, fluorine at 4.0. So this bond then would be one that is polar. And it's because they have different electronegativity values. Now, your textbook does go further, has a table right below this table of electronegativities, and says, well, actually, if we go between 0 and 0.4, we call it nonpolar. It goes from 0.4 to 2, we then call it a polar bond. And if the electronegativity value is greater than 2, then we say that that is an ionic bond. And I really don't care that you know this 0.4 value in here, because for it to be truly nonpolar, its electronegativity value should be identical or very, very close. So, and depending upon the author, you might see someone will call it 0.2, others will call it 0.5. It really is an arbitrary cutoff. So just for the sake of our argument, when it comes to our exams and when it comes to your homework, I've tried anyhow to make sure that it's very clear that if they're identical, then it is going to be a nonpolar bond. And then if it's going to be in this range right here, where there's a large difference, or a difference between them, then it's going to be a polar bond. And then if the difference is really, really large, then it's going to be an ionic bond. And the only time we have a really big difference between them is if we combine a metal with a nonmetal, and all along we've talked about them as being ionic bonds anyhow when we combine these metals with the nonmetals. The reality is, and this really only matters to chemists, it doesn't matter to you guys, the reality is that there's really no such thing as these bonds that are purely covalent unless they have identical electronegativities or pure ionic. The reality is that there's always some mixture between them. There's always some sort of blend. And if you get into more advanced chemistry, we might talk about something like the percent of ionic character. And so really there's never really anything that's truly 100% ionic. And there's never really anything that's truly 100% covalent unless we're talking about one where there's pretty much identical atoms bonded to each other. So if you are going to learn any difference, just know this one right here. That kind of 2.0 is that cutoff between ionic and covalent in terms of bonds. But even then, it's going to be ionic if you have metals bonded with nonmetals, and so there's really not much point to really even distinguish between them.